am going to explain about p-n junction diode. This subject is for first year students, second sem. Basically, materials are three types: conductors, semiconductors, insulators. Semiconductors are divided into two types: pure semiconductors, impure semiconductors. Again, these impure semiconductors are two types: n type and p type. Pure semiconductor material is doped with pentavalent atom, then n type is formed. Pure semiconductor material is doped with trivalent atom, then p type material is formed. For p type, example is aluminum. So atomic number is 13. What is the electronic configuration? 1s2, 2s2, 2p6, 3s2, 3p1. So outermost orbit is nothing but third orbit. So in this third orbit, number of valence electrons are 3. So silicon, suppose this trivalent atom is doped with silicon, or this silicon is doped with trivalent atom, then silicon atomic number is 14. So what is the electronic configuration? 1s2, 2s2, 2p6, 3s2, 3p2. So number of valence electrons are 4. So silicon contains 4 valence electrons. Aluminum contains 3 valence electrons. So in this aluminum, by using these 3 valence electrons, 3 covalent bonds are formed. What about the fourth one? Fourth one is nothing but vacant space. This fourth one is nothing but vacant space. This is known as hole. So it is in a position to accept one more electron from the neighbor atom. That's why these p-type materials are known as acceptors. Suppose silicon material is, or suppose this pure semiconductor material is doped with pentavalent atom like phosphorus. Phosphorus atomic number is 15. So what is the electronic configuration? 1s2, 2s2, 2p6, 3s2, 3p3. So number of valence electrons are 5. Suppose this semiconductor material is doped with pentavalent atom, then silicon valence electrons are 4, phosphorus valence electrons are 5. So by using 4 valence electrons, 4 covalent bonds are formed. What about the fifth electron? Phosphorus contains another fifth electron. This fifth electron is in a position to donate this free electron to neighbor atom. That's why n-type materials are known as donors. Now I am going to explain about how this p-n junction diode is formed, what is the working condition, and what are the applications of this p-n junction diode. First of all, take pure semiconductor material. What are the examples for semiconductor materials? Germanium and silicon. Pure semiconductor material, half of the part is doped with trivalent, half of the part is doped with pentavalent. Then p-type semiconductor material is formed, or p-n junction diode is formed. Half of the material is doped with p-type, half of the part is doped with n-type, then p-n junction diode is formed. So what is the symbol for p-n junction diode? Symbol for p-n junction diode is, this is the symbol for p-n junction diode. This is anode, this is cathode. Anode is nothing but, it contains two terminals, anode and cathode. Anode is nothing but positive terminal, cathode is nothing but negative terminal. So in this p-n junction diode, there are two types of p-n junction diodes are there: forward bias, reverse bias. What is meant by biasing? If you apply some external voltage to the p-n junction diode, then this is known as biasing. There are two types of biasings are there: forward bias, reverse bias. What is meant by forward bias? What is meant by forward bias? This is nothing but p-n junction diode. P-type is connected to positive terminal of the battery. P-type is connected to positive terminal of the battery. N-type is connected to negative terminal of the battery. Then p-n junction diode is in forward bias. So in the p region, majority charge carriers are holes. Holes contains positive charge. So these holes are repelled by the positive terminal of the battery, and these holes move towards the junction, and some of the holes cross the junction, then they become positive charged immobile ions. In the same way, in the n region, majority charge carriers are electrons. Electrons contains negative charge. These electrons are repelled by the negative terminal of the battery, and these electrons move towards the junction. Some of the electrons cross the junction, then they become negatively charged immobile ions. So these immobile ions opposes further movement of, so in the n region, positive charged immobile ions, in the p region, negative charged immobile ions are formed. So this region is known as depletion region. These immobile ions opposes further movement of charge carriers from P region to N region as well as N region to P region. So there is no any movement in the charge carriers. So current equal to 0. Current value equal to 0. Whenever the supplied voltage value is greater than the barrier potential, due to this immobile charge carriers or due to this immobile ions, some potentially developed in this depletion region, that potential is known as barrier potential. That potential is known as barrier potential. Whenever the supplied voltage value is greater than the barrier potential, from this point onwards, charge carriers move from P region to N region as well as N region to P region. From this point onwards, conduction takes place. So, whenever the supplied voltage value is greater than the barrier potential, from this point onwards, conduction takes place. That corresponding voltage is known as cut-in voltage. So, for silicon, this cut-in voltage value is 0.7 volts. For germanium, 0.3 volts. So, as VF value is increases, as forward voltage or applied voltage value is increases, current value is also exponentially increases. So, what is meant by reverse bias? Reverse bias is nothing but P type is connected to negative term of the battery, N region is connected to positive term of the battery. Then PN junction diode is in reverse bias. When PN junction diode is in reverse bias, in the P region, majority charge carriers are holes. Like charges are repel each other, unlike charges are attract each other. So, in the P region, majority charge carriers are holes. Holes contains positive charge. So, these holes are attracted towards the negative terminal of the battery. In the N region, majority charge carriers are electrons. These electrons contains the negative charge. So, these electrons attracted towards the positive terminal of the battery. So, in the P region, holes move away from the junction. In the N region, electrons move away from the junction. So, width of the depletion region at the junction point is increases. So, in the P region, not only the majority charge carriers holes, minority charge carriers electrons also available. These electrons are attracted towards the positive terminal of the battery. So, some of the electrons cross the junction, then they become positive charged immobile ions. In the N region, not only the majority charge carriers electrons, minority charge carriers holes also available. These holes are attracted towards the negative terminal of the battery. Some of the holes cross the junction, then they become negative charged immobile ions. So, width of the depletion region is increases. So, whenever PN junction diode is in reverse bias, so current is due to minority charge carriers. That is in the order of microamperes. Whenever PN junction diode is connected in forward bias, current is due to majority charge carriers. That is in the order of milliamperes. So, when PN junction diode is connected in reverse bias, current is due to minority charge carriers. This current is also known as leakage current. So, as VF value is increases, VR is nothing but reverse voltage. This voltage is denoted as VR, means whenever PN junction diode is in reverse bias, that voltage is denoted as VR. As VR value is increases, more number of holes are attracted towards the negative terminal of the battery, more number of electrons are attracted towards the positive terminal of the battery. So, width of the depletion region is increases. As VR value is increases, width of the depletion region also increases. Next one is VI characteristics. VI characteristics gives the relation between voltage and current in forward bias as well as the reverse bias. So, by taking VF value and x-axis, IF value, VF is nothing but forward voltage, IF is nothing but forward current, VR reverse voltage, IR reverse current. So, by taking VF and IF, these two are positive values. So, these two are taken in first quadrant. VR and IR, these two are negative values. So, this reverse voltage and reverse current, these two are taken in third quadrant. So, by taking forward voltage on x-axis, forward current IF and y-axis, as forward voltage value is increases up to certain point, current value equal to 0. Up to certain point, current value equal to 0. This is due to immobile ions. There is no any movement in the charge carriers from P region to N region as well as the N region to P region. So up to this point, the supplied voltage value is less than the barrier potential. Whenever the supplied voltage value is greater than the barrier potential, from this point onwards, conduction takes place in P junction diode. So charge carriers move from P region to N region as well as N region to P region. So from this point onwards, as Vf values increases, current value is also exponentially increases. Whenever suddenly rises in the current value, that corresponding voltage is known as cut-in voltage. This is denoted as V gamma. That value is 0.7 for silicon. That V gamma or cut-in voltage value is 0.3 for germanium. This is nothing but PN junction diode forward VI characteristics. PN junction diode forward biased VI characteristics. Next one, PN junction diode reverse bias VI characteristics. VI characteristics gives the relation between reverse voltage and reverse current. VR reverse voltage, IR reverse current. This current is in the order of microamperes. So by taking VR on negative x-axis, IR on negative y-axis, as VR value is increases, as negative VR value is increases, IR value is also increases up to certain point. From this point onwards, as VR value is increases, IR value is constant. Reverse current value is constant. This current is known as reverse saturation current. This is denoted as I naught. This is denoted as I naught. From this point onwards, as VR value is increases, reverse voltage value is increases, current value is suddenly increases. Or at this point, as VR value is increases, up to certain point, IR value is also increases, but IR value is constant. IR value is constant. This corresponding current is known as saturation current. This is denoted as I naught. At this point, as VR value is increases, junction breakdown takes place. From this point onwards, current value is increases. Whenever breakdown takes place, that corresponding voltage is known as breakdown voltage. That corresponding voltage is known as breakdown voltage. It is denoted as V beta. So here, breakdown is due to two effects. One is nothing but avalanche breakdown. Second one is Zener breakdown. What is meant by avalanche breakdown? Avalanche breakdown is due to carrier multiplication. What is meant by carrier multiplication? What is meant by carrier multiplication? As VF value is increases, as VF value or as VR value is increases, reverse voltage value is increases, velocity of charge carriers also increases. Whenever velocity of that electron is increases, kinetic energy half m square is also increases. Whenever kinetic energy is increases, that much of energy that electron is collide with neighbor atom. Then free electrons are. So whenever this free electron is collide or bombarding with one covalent bond, two free electrons are obtained. Whenever these two free electrons are collide with another two covalent bonds, then you have to get 4 free electrons. Again, from this 4 to 8, from 8 electrons to 16, from 16 electrons to 32, 32 to 64, 64 to 128, like that. So, number of charge carriers or number of free electrons increases. This is known as carrier multiplication. So, whenever PN junction diode is in reverse bias, that breakdown is due to carrier multiplication. That breakdown is due to carrier multiplication. That breakdown is known as avalanche breakdown. Avalanche breakdown is due to carrier multiplication. Zener breakdown is due to high intense electric field in the depletion region. Zener breakdown is due to high intense electric field in the depletion region. So this is nothing but VI characteristics of PN junction diode. Next one is diode resistance. By using Ohm's law, V equal to I into R. So from this formula, R equal to V by I. Or from this VI characteristics, how can you define dynamic resistance and static resistance? So in this, whenever PN junction diode is in forward bias, from this forward VI characteristics, on this operating region, if we consider any point, suppose P, Q, from this point, if you consider any operating point, suppose that particular point equal to Q. From this particular point Q, what is the corresponding voltage? You can draw one vertical line on this x-axis, that corresponding voltage is equal to suppose V1. From the same operating point Q, you can draw one horizontal line on y-axis, that corresponding current equal to suppose I1. Now, static resistance, capital RF. Static resistance, capital R equal to corresponding voltage by corresponding current. So, V1 by I1. From the PN junction diode forward bias VA characteristics, on this operating point, on this operating region, if you consider any operating point, from this operating point, you can draw from one vertical line x-axis, corresponding voltage is equal to suppose V1, or suppose that value equal to 10 volts. From the same point, you can draw one horizontal line on y-axis, corresponding current equal to suppose 2 milliamperes. Now, what is the resistance value? Static resistance equal to, what is the corresponding voltage? 10 volts, corresponding current equal to suppose 2 milliamperes. So, 10 volts by 2 milliamperes, milliamperes is nothing but 10 by 2 into 10 power minus 3. That is nothing but static resistance. How can you calculate dynamic resistance? Dynamic resistance is nothing but reciprocal of slope of this curve. How can you calculate slope for this curve? Slope for this curve is nothing but m equal to y2 minus y1. Reciprocal of slope of this curve is nothing but dynamic resistance. Dynamic resistance is denoted as small rf. This rf is nothing but delta V by delta I. How can you get this delta V by delta I? For this curve, calculate slope value. How can you calculate slope m? Slope m equal to y2 minus y1 by x2 minus x1. So, y2 minus y1 is nothing but, you can draw one vertical line on y-axis. Suppose this is the VA characteristics when our PN junction diode is in forward bias. So, for this curve, calculate the slope value. How can you calculate slope value? This is the slope. How can you calculate slope value? Corresponding voltage is, suppose this point is, from this point you can draw one vertical line, corresponding voltage is equal to suppose V1. From this point you can draw one vertical line, corresponding voltage is equal to V2. Corresponding current is I1, corresponding current equal to I2. Therefore, here delta V equal to V2 minus V1, delta I equal to I2 minus I1. Therefore, M equal to V2 minus V1 by I2 minus I1. RF equal to reciprocal of slope of this curve. So, 1 by M. 1 by M is nothing but 1 by I2 minus I1 by V2 minus V1. So, this is nothing but delta V by delta I. Here delta V is nothing but V2 minus V1. Delta I is nothing but I2 minus I1. So, reciprocal of the slope of this curve is nothing but dynamic resistance, small RF. Next one is diode capacitance. So, there are two types of capacitance are there, diffusion capacitance and transition capacitance. This diffusion capacitance is considered when our PN junction diode is in forward bias. Transition capacitance is developed when our PN junction diode is in reverse bias. Suppose when our PN junction diode is in forward bias, how this diffusion capacitance is developed or how this diffusion capacitance is defined when PN junction diode is in forward bias. PN junction diode is in forward bias means P type is connected to positive terminal of the battery, N type is connected to negative terminal of the battery. So, in the P region, major charge carriers are holes. These holes are repelled by the positive terminal of the battery, and so these holes move towards the junction. Some of the holes cross the junction, then they become positive charged immobile ions. In the same way, N region is connected to negative terminal of the battery. So, in the N region, majority charge carriers are electrons. These electrons are repelled by the negative terminal of the battery. So, some of the electrons cross the junction, then they become positive charged immobile ions. So in the depletion region, not only the majority charge carriers, minority charge carriers, some excess charge carriers also move from P region to N region as well as N region to P region. Due to this, excess charge carriers in the depletion region, some charge is developed. The charge is suppose denoted as dq. As VF values increases, charge developed in this depletion region is also increases. As applied voltage value is increases, charge developed in this depletion region is also increases. So here capacitance is defined as CD is nothing but diffusion capacitance. Here D indicates diffusion. So CD equal to dq by dV. These two are directly proportional. As VF value is increases, charge developed in this depletion region is also increases. Therefore, CD equal to dq by dV. Another formula for CD equal to tau I by eta Vt. How can you derive this tau I by eta Vt? CD equal to diffusion capacitance CD equal to tau I by eta Vt. Where tau is nothing but carrier lifetime, I is nothing but current passing through the diode, eta is nothing but efficient coefficient, Vt is nothing but voltage equivalent temperature. This Vt value, voltage equivalent temperature value is 26 millivolts. Now how can you derive CD, diffusion capacitance CD equal to tau I by eta Vt? Tau I by eta Vt. So what is the definition of the CD? Diffusion capacitance is nothing but dq by dV. So here again charge q is nothing but q equal to tau into I. I is nothing but current passing through the diode. Tau is nothing but carrier lifetime. Tau is nothing but carrier lifetime. What is the current equation? I equal to I naught into e power v by eta Vt. Current equation I equal to I naught into e power v by eta Vt minus 1. Here I naught is nothing but reverse current. So forward current is denoted as IF. So I equal to I naught into e power v by eta Vt minus 1. Whenever PN junction diode is in forward bias, applied voltage value is positive. Whenever applied voltage value V is positive means this exponential term becomes positive. Whenever this exponential term becomes positive means then you can neglect this one value. This one value is very less than e power v by eta Vt. So you can neglect this one value. Then I equal to I naught into e power v by eta Vt only. So therefore IF equal to forward current, diode forward current, IF equal to I naught into or IF into e power v by eta Vt only. So I equal to I naught into e power v by eta Vt. Now differentiate this current equation with respect to V. So di by dV equal to current equation I equal to IF or IS into e power v by eta Vt. Now differentiate this current with respect to V. Therefore di by dV equal to IF into e power v by eta Vt. Then you can differentiate this exponential term with respect to V. Then 1 by eta Vt only. 1 by eta Vt only. So I equal to I naught is nothing but constant value. So I equal to I naught into e power v by eta Vt into 1 by eta Vt. 1 by eta Vt. So current equation I equal to I naught into e power v by eta Vt minus 1. Whenever PN junction diode is in forward bias condition, IF equal to V is nothing but applied voltage. So forward voltage value is always positive. So this exponential term is also positive. Whenever this exponential term is positive means you can neglect this one value. Then IF equal to I naught e power V by eta Vt only. Now differentiate this equation with respect to V. So di by dV equal to I naught e power V by eta Vt. Differentiate this exponential term with respect to V. 1 by eta Vt only. Here I naught into e power V by eta Vt is nothing but current equation I. Therefore I by eta Vt. So diffusion capacitance CD equal to dq by dv. Again q equal to tau into I. Here tau is nothing but constant. CD equal to dq by dv. Now substitute q value. Q equal to tau into I. Here tau is nothing but carrier lifetime. This is nothing but constant. Now differentiate this equation I equal to I naught into e power v by eta vt minus 1 with respect to v. Then this becomes I naught into e power v by eta vt by eta vt. I naught e power v by eta vt is nothing but current equation I. So then this becomes tau I by eta vt only. Next one is transition capacitance. So in this one, whenever PNX diode is connected in forward bias means this P region is act as one parallel plate of the capacitor, N region act as another parallel plate of the capacitor. So in between these two, this depletion region act as dielectric material. So some capacitance is developed whenever PNX diode is in forward bias. That capacitance is known as diffusion capacitance. P region is act as one parallel plate of the capacitor. N region is act as another parallel plate of the capacitor. In between these two, depletion region will be there. This one act as dielectric material between these two parallel plates. So some capacitance is developed in this PNX diode whenever this is in forward bias. Thus, that capacitance is known as diffusion capacitance.